And since I see a few new faces, I introduce the speaker. So, speaker today is Professor Miguel Alonso, and he has been giving this series of 3 talks: QuIC Talk, Quantum Information, and Coherence talks. These are supposed to be at very informal level. So again, anybody have a question, you can feel free to interrupt and ask questions. So, Professor Alonso received his degree of engineering in physics from University of Autónoma Metropolitana in Mexico City.
Very good.
And the PhD degree in optics from University of Rochester. He joined the faculty of the Institute of Optics, Rochester, in 2003, and 2008 he moved to France, where he joined the Institute of Univ and centroid Marseille. And he's currently a professor there. And since January 2020, he's also serving as the editor-in-chief for Optics Letters, as well as the director of research at Central Marseille. He's also a fellow of Optical, formerly Optical Society of America. His research focuses on mathematical aspects of wave propagation, in particular on the description and applications of beams with structure intensity and polarization distributions, optical coherence, and the connections between wave and wave models of light. So with that,
well, thank you very much, Alan. Thank you everyone for putting up with me for a 3rd time in a row. Today I'm going to continue talking about rays and waves, and I'm glad you reminded me that this series is on coherence and quantum information. Coherence, there will be coherence today. Quantum information, not so much. But some of the techniques that I will describe today are techniques that are used also to study quantum optics. So there are many analogies with that. So I'm going to continue with the topic of connection between rays and waves, but today from a very different point of view. The mathematical corresponds to bilinear transformations proportional to more to the intensity than the field, which is what we discussed in the last couple of days. I had not finished one part of my previous presentation. I decided to leave that till the end because I'd rather cover this topic and not that if we don't get to it. So if we're going well, I'll go back and discuss that last case. So the title on this slide is Wave Optical Coherence and Phase Space. So there will be rays, don't worry. The first time I gave a form of this presentation was for an audience that were in digital photography, so not quantum optics people at all, let's say. And in digital holography, there's a concept they use that is unfortunately called the light field, which is not the field, it's not the light field, is something like what we call in optics the radiance, or the specific intensity, or what could be also called things, well, there are many possible definitions from the wave point of view, like the Wigner function. So the Wigner function is going to be the main thing I'm going to be talking about in some way, but I'm going to talk about coherence for those of you who are not so familiar with coherence. I'll try to give you some intuitive ideas. Now, so this light field is a 4-dimensional function, and it's a ray optical concept. Coherence is a wave optical concept and it's a 4-dimensional function, but it's different 4 dimensions. So I wanted to talk about these different 4 dimensions and see what the connection is. So I'm making here a reference to this book that you might have read. It's a classic book, Flatland. It's a short novel. Is Edwin Abbott. It was from the time of Alice in Wonderland, that type of literature. So it's more of an allegory of social dynamics, but of the time. But it has some nice geometry, and it's about a world that is 2-dimensional, and then at some point, the 3-dimensional being comes and interacts with this world and all the things that change. But it's been used a lot in relativity and other aspects to motivate people to think about more dimensions that you can experience. For us, something in 4 dimensions would have a similar impact than the 3-dimensional thing to this 2-dimensional universe. I also make reference to it because to illustrate some concepts, I'm going to restrict myself to Flatland, that is to the screen here. It's two-dimensional. It's much easier to draw in 2 dimensions than in 3, never mind in 4. Okay, so what are the 4 dimensions from the ray point of view? And this is related to things that we discussed already. So suppose that we have a ray traveling in free space, and at some initial plane I want to specify uniquely this ray. How many numbers do I need? Well, I need to say what its initial x and y coordinates are, but I also need where the ray is going. So, and that I can specify a tilt in x and a tilt in y, for example. So if I take a segment of this ray that is of unit magnitude and I project that onto the initial plane, I have this little segment here which has some coordinates. And those coordinates tell me the direction of the ray. So I need 2 planes, one for x and y, and one for what I call px and py, which are the direction cosines of this ray. Much of what I will do is in the Bragg's approximation, so whether this is the sine of the angle, the cosine of, the sine, the tangent is the same thing, or the angle itself. So we need 2 coordinates and 2 directions. Another thing that I want to stress here is, let me move my ray a bit down here, is that, no, actually I will do that later, but yeah, I can show it here. So what happens if I keep talking about the same ray, but I want to look at a different plane? What's going to happen to these points? Any of the students have a guess? Will they both change? Will none of them change? Just position. So if I slide this, position changes linearly to momentum. Momentum doesn't change because we're in free space. Free space does not bend light. So let me go to Flatland and think of the same thing. So again, now I only need 1 coordinate and 1 direction. So I have, I can put some coordinates and 1 direction. And again, if I propagate, I can see that the position changes proportional to the direction. So I need these 2 axes, position and direction. But now I can see the convenience of building what is called a phase space, which is an artificial space where you mix axes that in a way don't belong together. And well, why don't I represent this instead of 2 lines by 2 coordinates of a point? So that's what we call the phase space. It's this space where one axis is the direction, the position, the other one is the direction. And this point represents this ray at this position. If I go to the initial plane, it is this point. So, so what happens again if I propagate in C? What's going to happen to this point now that I see it this way? It's going to move to the left or to the right if I propagate. It's going to, yeah, it's going to go like this. But what if the inclination of my ray were like this? Now what will happen to the point as I propagate? It will go to the left. In what circumstance will the ray not change the position? When the direction is flat. In this case, no change. So we can see that as we propagate, stuff that is up here moves to the right, stuff that is down here moves to the left, and the further away from the axis, the more that happens. So that is a linear transformation called a shearing. It's like we take this space and we do this transformation. Now, this is easier to understand in Flatland because in real space we have a 4-dimensional phase space, x, y, px, and py. And we still have a point in this space that is hard to picture, but we can describe it mathematically, and it will also shear. It's just a shear in four dimensions. So the radiance or the light field is a concept of more of incoherent light, like this scene, like something that we see in everyday is not the light of a laser, is an incoherent light. So suppose that I have a distribution of point sources or something, each one is generating its own light, and there is no interference between. So really, I should think of all the possible rays, not just a selected family of rays like in the last lectures. I have to think of all the rays from all the positions, or with all the directions. So with this I can actually fill up the space. And here I'm painting in green the rays that carry more light, for example. And I put the same thing here. So this black point, it means that the ray is carrying no light. But this one is carrying a lot of light, etc. And of course I'm sampling here. In reality, I have more of a continuous distribution here. It's a continuum, two-dimensional continuum of rays. But to represent things, let me use this sample measure. So each one of these points is one of these rays. What is the intensity that I observe? So here I plot the intensity, which is a function of the horizontal axis, which is position. So it's what I would measure if I put a detector at that plane. Can I relate that to this distribution? So what I need to think is, I go to a given point, and I look at all the rays that hit that point, and I integrate. And that gives me the total light. That corresponds to coming to a given point. I look at all the rays with that position, and I integrate. So I do what is called a marginal projection. I integrate vertically, and that gives me the intensity. Yes?
Ex is essentially a spatial frequency, right? You can do it in that
fashion. When we go to waves, it will be. But for now, in the ray world, there's no frequency in the wave. So it's a direction. But yeah, once you put the wave aspects, it does correspond to spatial frequency, especially if we're talking about coherent light. So now what if I propagate my plane? So I don't look at the initial plane, but at some plane here. But what we'll have is the shearing of the space that I mentioned before. All the rays will displace rigidly, some to the right, some to the left. And the intensity will evolve because I still need to do a vertical projection, but now different rays are entering that vertical projection. So in a way I can compute the evolution of intensity not by doing diffraction integrals, well, because we're not in the wave domain, but by just doing a geometric transformation of this phase space and projecting that. So this is the basic idea, essentially, of a light field. So again, photographers and others call this the light field. I would call it a phase space distribution for the field, and it's sometimes called the radiance or specific intensity. Questions? Is that clear?
So,
yeah.
So in this kind of a picture, like if you put some optical elements like glass plate lenses, how does shearing change?
Yes. So for simplicity in this presentation, I'm just thinking about free space. But if you put a lens, a thin lens, you can convince yourself that that is a vertical shearing. So a lens would do this, because at each plane, the position would not change, but the direction would change, and would change more the further away you're from the axis.
It's like a twist.
Yeah, so you would go, so for example, if you start with some distribution of phases, which I'm going to represent with a rectangle, and you propagate, then you get to something like this. My drawing doesn't represent it, but this has the same area as this. This preservation of area is a key thing. It's equivalent to Liebel's theorem in mechanics. is something called the conservation of étendue. Is a fundamental quantity that has to be preserved. So this free propagation, if I put this in a lens, for example, I can do a shearing like this. So after a lens, let me identify my corners, 1, 2, 3, 4, 1, 2, 3, 4. If I use the right lens, for example, I can do this. These 2 points are at the axis, they're not going to move. This one's going to go down, and this one's going to go up. I choose the right focal length. This will come to something like this. So this is 1, 2, 3, 4. And now notice, if I let it propagate again, I can come up to something that is rectangular again. 1, 2, 3, 4, but is rotated. This is a Fourier transform. I change what was position is now direction, what was direction is now position. You can do something with different distances to show how to form images. So I actually find this sequence of transformations as a very intuitive way to understand the effects of optical systems. Things like gradient index waveguide, those would do rotations with a given scaling because this axis and this axis don't have the same units. So there's a series of elements that correspond to simple linear transformations. If you have aberration or something, then straight lines will no longer be straight lines. You will mess up the faces. But still preserving areas. Yes?
So when you said this is a Fourier transform,
Sorry?
when you say this is a Fourier transform,
Yeah, it will be a Fourier.
there's no phase anymore, right?
No, in fact, I'm talking about rays. So this is the ray optical view of a Fourier transform. Because a Fourier transform, what you do is you go from looking at the local distribution to looking at the directional distribution, the spatial frequency distribution. So here if I project, this is x, but here if I project, I get in x what used to be in p.
But this is still completely ray optics.
It's completely ray optics. So calling it a Fourier transform is
In that it still cannot accommodate a phase.
yeah, it's exactly. So let me put it this way. When we see this from the wave point of view, this will be a Fourier transform. And this is the optical system, the 2F system that actually does a Fourier transform. But you can picture a Fourier transform in this ray domain as just a rotation of the phase space.
But the phase is inbuilt, right? In the sense that the scales is actually a physical
Yeah.
change of a scale
Yeah.
as it propagates. So the dynamical phase is captured in this area.
Yeah, yeah. So once we see how to write wave things on that language, whatever form I have of this distribution, the phase is hidden in there. Yeah. Yeah.
But also, I guess those little patches are usually included as sizes of lambda and so on.
Yeah. So for now, I'm living in the naive photographer's world of diffraction doesn't exist, and so yeah, these are tiny. But when we go to heuristic, yeah, the minimum uncertainty cell is and that's why we'll see later in the wave phase space, it doesn't make sense to talk about what is happening at one point. It's not something we can measure.
But with the shear and rotation picture, you can also think, like, imagine how a beam is, Gaussian beam, for example, is getting compressed at the focal point.
Absolutely, and we will, yeah, exactly. So this is something that we've run at your lab a few times in the last few days. Is I'll show that example, but yeah, of course, here my phase space thing is blocked like this. The spatial extent is this, but if I let it propagate, it will be something like this. The angular extent does not change, but the spatial extent changes. And we introduce a correlation of position and direction, which means that in this part of the beam, the rays are going more that way. In this part of the beam, the rays are going more that way, because the wave is diverging. Yes?
So here the point sources are distributed in uniformly.
Yeah.
So, but your image has a asymmetry in the intensity profile, and also your initial figure had a too low kind of thing.
Yeah. So about this uniform thing, really I meant to draw this as a continuum. But if I draw a continuum, we wouldn't see nothing. So this is a sampling of a continuum of rays.
But,
So these effects like this is just an artifact of my sampling.
but your intensity profile should be symmetric.
No. If you see these rays on this side, there's more green here than here, for example. So it's hard to see, but there's an asymmetry here. So if I come at the beginning and look at a given ray, let's say this ray here, this really I made sure that this corresponds to the same green as I have in the corresponding dot. So the properties of this distribution, and this is nothing to do with waves yet, is this shearing property that if you propagate, you can express this expression simply as a remapping of the arguments of the initial one. We don't need to do integrals for propagation. It's just messing up with the arguments in a linear way. And the other one is the marginal property that if I integrate this in direction, I get the position distribution. I didn't write it, but if I integrate in position, I get the direction distribution. Okay, so how do we measure this thing? It's a problem, but there are instruments out there that try to do this. And again, when we get into the wave details, they have all sorts of imperfections, but in the naive ray vision, they sort of work. And two that are sort of equivalent are the Sharp-Hartman sensor and something that is called a planoptic camera or a light field camera. The only difference between them is a big lens in front for the planoptic camera. The Sharp-Hartman is just an array of tiny lenses with a CCD detector or CMOS or whatever detector behind it, such that there's many pixels assigned to each lenslet. So we can think of the lenslets as position pixels, and the pixels behind each lens as direction pixels. Why? Because if I have a ray that hits that is horizontal and moves to different positions, if it is horizontal, it will always hit the center pixel of behind each detector. So I just move. So I take these pixels and I rearrange them in position versus direction, and this is like a phase space now. So this is at the center and it's flat. If I now change the direction, then I would be hitting a different pixel here. That doesn't change much if I move within the lenslet, but then if I go to the next lenslet, I move horizontally in the phase space. So this is a way to discretize position and direction, phase space, and try to sample it. In this case, my CCD detector is one-dimensional. My phase space that I want to sample is two-dimensional. So it's impossible to really sample it completely. In real life, the detector will be two-dimensional. The phase space is four-dimensional, so it's impossible. But we can sample. And this is a trick to do this. And so the planoptic camera, which they were very fashionable for a while, and I don't know if the fad has passed a little bit, but it's a type of camera that you can take a photo and then refocus it afterwards, because it's capturing all this. So I will explain how this refocusing works in a moment. So imagine that you capture with a camera like this image, and then to get the image, what you have to do is project down. But suppose that you want to pretend, oh, actually, what happens if my image were a bit further away? Well, I could shear my sample phase space before doing the projection. And there's all sorts of numeric things that you have to do that, but this would let you get images corresponding to different focal distances. Yeah, there's no free lunch. Yes. And talk about free lunches. These cameras are really expensive, so there's really no free lunch. The Lytro was one that was quite popular. I think LYTRO. So how does this refocusing works? So again, consider a flatland scene where this is my space here, and I have three objects: this line, and this line. This is the distance, the focal distance, the depth, and this is the transverse position. So if I use my planoptic camera, I would capture a phase space distribution something like this. And then to get the image, I need to project down. So notice that because this object is at the nominal focal distance, all the rays coming from it have the same position, so this is vertical, this is vertical. If I do the projection down, I get this image. And Mathematica in this new version messed up with my scale. Yeah. Let's see if I put as it was before. Well, that's smaller, but it is more correct. So this falls here. I project this, and I get this thing here. But these ones look blurry because if I project this down, well, there's these ramps end up being blurriness at the ends, and this one as well. So how do I focus after taking that photo? How do I focus on the other object? I can simply shear the phase space, and I shear all those. So when I focus on this guy, for example, now this one's sharp, and its projection is nice and clean. So if you go to YouTube and look for planoptic camera or light field camera, you'll find all these movies of a photo that they change this, and you see how like they always have like a sequence of people at different distances and how it focuses on different. I think people have been using this for 3D tracking as well in experiments.
Sorry,
yeah.
Have people used this for microscopy, for example?
I think so. I think they tried. I don't know if I think in that conference I heard someone talk about it, and I would guess probably someone like Clara Waller or someone like that would have tried this, but I'm not sure. I will look into it, but I'm absolutely sure that they yeah. Yeah.
So depending on how you're gridding the camera,
Yeah.
and your grid spacing, your PX PY might not always be independent. They might be coupling artificially because of it.
So say that again.
Your PX and PY,
Yeah.
they might not be completely independent.
Yeah. So
Some artificial coupling.
yeah, especially in the paraxial regime they are, but when you go non-paraxially, they start to couple because you have some signs are not tangents and
You need very fine grid.
yeah, that's right. And I think some of these cameras have hexagonal arrays of lenslets, which makes it more fun for the programming part of the thing. By fun, I mean a nightmare, but challenging, let's say. But the principle is that. So that was the ray optical four-dimensional space. So now I'm going to talk about the wave optical four-dimensional space and see conceptually how we can bring it together. So we know in free space that we have now, I'm going to start with a purely coherent field. If I do the usual gains from Maxwell's equations, ignore polarization, I get to something like the Humboldt's equation. But if I talk about partially coherent fields that have rapid fluctuations, I can no longer talk, no, not yet. First, if I know this field at some initial plane and I want to know it at a different plane, a different point, I need to do a diffraction integral. So where this is a propagator, Huygens, Fresnel propagator, the Rayleigh-Sommerfeld propagator, depending on the level of sophistication that you want. But it is a double integral. You have to integrate over the initial space to go to the final space. Yes?
Sir, one question from previous slide.
Yeah. Yeah.
So in this case, yeah, you were sharing this space, so kind of bringing the object in focus.
Yeah.
Kind of.
Yeah.
So in theoretically, you can change any range is very large in this means.
Yeah.
Yeah, 90 degree is in.
Yeah. So.
Yeah, in practical, there should be some limit.
Yeah. So for example, here I cheated in that I kept these edges straight. But in practice, there are some edges, those they will tilt too.
Yes.
And you can see that at some point, you will have no overlap region between things. And well, of course, then you will start not being able to do things appropriately.
And last, in practical, many scenario you have means X, Y, and Z also is there, right? In
Yeah.
depth. So can we go to the 6 dimension in that way or?
Yeah, the good thing is yeah, fundamentally that's a very good point that you raised. Why do we make Z special? We have X and Y and Z. What I would say is that for specifying the direction of a ray, you need a direction vector that is normalized. So that means you normalize it to 1, so only 2 of its components are independent. So you only need to specify 2 components, and the third one is automatically specified. So we choose PX and PY because we're pointing the camera mostly in one direction, so we make Z special in that sense. We can calculate the Z component from the square root of 1 minus the X and Y components. We choose the plus sign for the square root because of the direction of light. So that's why 2 dimensions are sufficient. And if we went to the 6-dimensional phase space, we would only live in some shell of that. Most of the space would be empty.
In this case, we can correct means X and Y means if something is not focused in X or Y.
Yeah.
So
So
there is problem in Z as well. Means
yeah, but that's what this shearing is helping us to do. Is by shearing the phase space, we select the Z that we have. We cannot completely not see this guy, and this guy. We see them blurry. And if you were to shear, if they were very small objects, and you were to shear a lot, then these would be very thin, and this would be very, very, very faint. Yeah. Okay, so what about the way, so partial coherence. So when the field fluctuates rapidly, we cannot measure what the field is at any given instant. But if it is stationary, like sunlight is extremely complicated, the evolution of what the electric field is doing at each time. But if I look at it with my eyes that integrate over some time, it looks pretty boring. It looks very uniform. So this is something that is highly fluctuating, but is stationary on averages. And this type of fields we can describe very well with this theory of partial coherence, where what we measure is not the field itself, but the field times its complex conjugate, even at 2 different points. We can get access to this correlation between what the field is doing here and what the field is doing here. And we call this a mutual intensity or a cross-spectral density function. It's a correlation of what the field is doing at this point and at this other point. Because it's a correlation of 2 fields, of the field at 2 points, and because each field would propagate with a diffraction integral, to propagate this thing, we will have to integrate over, we have to propagate in each set of variables, so we have a double propagator here, and we have to solve a 4-dimensional integral. And these propagators have highly oscillatory exponents, so numerically this is a bit of a nightmare. As I think you guys have tested. You even have done the 8-dimensional version, so that's even worse. Okay.
So the averaging is the ensemble average.
It's an ensemble. You can think of it as an ensemble average or a time average if
But they are not necessarily ergodic.
if they're not ergodic, then yes. But I think from a practical point of view, when I'm doing integration with a detector, is really integrating over a window of time. So this function, again, because we only need to specify the field, an initial field, and from there we can take it somewhere else, it is enough to know this field at the initial field. So we need 2 coordinates for R1 and 2 coordinates for R2. And those are the 4 dimensions, again. But there are very different flavor of 4 dimensions. So how do we measure this coherence function? And this is a cross simplification. So suppose that I have some source. In this case, I chose a finite source that is spatially incoherent. And to measure the coherence between this point here and this point here, so now it's a 2-dimensional function because of Flatland. I let the light go here and interfere here, and I see some fringes. And these fringes will depend on many factors, but it depends on the separation between the 2 points. And what I care about more than the period and the specific location of the fringes for now is their what is called their visibility. So there, if the, do I have a slider for the source size? Yeah. So if the source is very small, the fringes are very visible. But if I make the source bigger, the fringes get smaller, and that means that there's less correlation between what happens at this point and at this point. Of course, the closer the 2 points get, the more coherence I get. And for some distances, there can be an anti-correlation. So here, for example, you can see that there's a reversal of the fringes. That means that the field at the 2 points is correlated, but it's really anti-correlated. So statistically, if we're at a crest in one point, we're at a valley in the other. So, how many of you don't know coherence? So to explain this concept, I like using this movie. And so this is a strange story. This is the shortest publication I have ever been an author to. This is someone else's work. This is from here to here, and this was with Emil Wolf and with Wayne Knox, who was the director of the institute back then. And it all started because Wayne had, next to where he lived more in the countryside. And maybe what I'll do is go straight to the movie. So next to his house, and it's in the countryside, there was this little pond. And he kept some ducks that lived there. So, and one morning he got up really early in the morning, and the water was pristine, very, very quiet. So he to protect his duck, he had a shed where they sleep at night. So it's early in the morning. He's looking around. There's the shed. So I'll go quickly because it's an unnecessarily long video. He gets closer. The ducks realize he's coming. And they really want to get out. There they go. They can't wait to go to the water. And now, let me freeze that there. And this is an oversimplification of the physics, but it transmits the message. And maybe before discussing this, let me ask the students, or everyone, a question. Suppose that you have some field that creates some coherence, and that this coherence is, the field is very incoherent, that is, you don't have to separate the points much before the coherence is lost between the 2 points. Now you get further away, sorry, you're looking to the, you get further away from the source, light goes from left to right, and then is the coherence width, the distance that the points have to be to keep some coherence. Is it bigger or is it smaller? Do you have more spatial coherence or less spatial coherence as you go away? More? Everyone's saying? So the ones that know the answer, but the recently I gave this something a lecture like this, and I said, please, the professors don't answer. Let the students. And I asked the question, and the professor stood up and said the answer. Is like, no, come on. You get any consensus? You get more coherence. So things get more coherent as you go. And the example here is each duck is a point source. Let's think that the wave comes because they're kicking. And they're certainly not agreeing on how to kick. So they're creating waves. And right here I have waves from this duck, from this duck, to this duck. They come from very different directions. And you can see that the shape of the waves is very irregular. That is a symptom of the fact that there's a lot of incoherence. It's hard to predict what the water is going to be doing here, given that I know what it's doing here. Now I let things settle down, the waves start to expand all over the lake, and get some more stationary conditions, and I go and look at the water far away from the ducks. And look at these beautiful uniform wavelengths. So as I get further away from the ducks, the waves get more and more uniform. So that is something, it's a concept of something called the Van Sitter-Zernike theorem, which I will try to explain with a simulation of the ducks. So go back here. No, it's down here. I left the code. So this is a simulation of the ducks. And this is generated at random. Each duck has a slightly different frequency and a slightly different position. So let me run that again because there are too many ducks on the same point there. Oh, I thought I let it be random. Anyway, so look at the waves, and now I see that indeed waves are much more coherent here, much more chaotic here. But if I get away, the wavefronts get very, very, very uniform. There are some nodal lines here, but those will fluctuate in time as I let time go. So I see the evolution of the waves. And when I average in time, this distribution of waves is going to be more or less uniform. But the distances over which there is correlation between the waves is big. What really matters is the angle that the source obtains from the points where you're evaluating this approach. That is really what matters. The smaller that angle, the more coherence you have. And of course, you can make the angle smaller by asking the ducks to get together or by getting far away. So I'd like to use this picture also to explain the difference with a laser or with a coherent source. And I like to say that I think my friend Wayne is a very bad trainer of ducks. If he were a good trainer of ducks, he would tell his ducks, okay, get information. And then 1, 2, 3, 4, start kicking. And now we would have a nice wave that would be very directional. If he were even better, he would tell his ducks to kick strongest if they're close to the center, less and less and less and less as they get away. And ducks would produce a beautiful Gaussian beam. So coherence not only, so we'll learn a few aspects of coherence here. Not only does it have to do with Van Sitter-Zernike, that the further away you're from the source, the more coherent the field gets, but also coherent emission can be much more directional than incoherent emission. It's an inherent thing. Incoherent emission tends to go everywhere. Coherent emission tends to be directional. Is that clear? So if I go back to the, actually I don't need to go back. So this is reflected here. If I change sorry, this is the centroid. If I change the separation between the two positions, there's some distance at which I will lose coherence, more or less. But if I go further away from the source, having trouble, my eyes are not as good as they used to be. If I move this further away, the coherence width gets bigger. But in any case, what I want to now do is connect this concept of coherence with the ray picture. And for that, I'm going to go to a different coordinate set, which is centroid and difference. So instead of saying point 1 and point 2, I'm going to say the average between the points, the centroid between the points, and the separation between the 2 points. And I'm going to talk about the coherence function in this way. So now my sliders are the centroid of the 2 pinholes and their difference. And that has an advantage because if I come and look at that here, suppose that I have a source like this, and there's some coherence width at the source. So this represents the coherence width. And suppose for now that as I move at different centroids, the coherence width is more or less the same. I also know that.
Sorry, now, what are you doing here?
So this is the intensity of the source, and this is sort of the coherence as a function of separation. So, and this coherence width, I can sort of think of it as some independent beam. And this partially coherent field is like an incoherent superposition of these coherent beams. I know that if I make my coherence width bigger, as in the coordinated dots, what happens to the field that's going to come out of here? Is it going to get more directional or less directional? More directional. Yeah, so if I make this bigger, it gets more directional. And if it gets smaller, it gets less directional. So this gives us the idea that, well, to look at what happens in position, let me look at the centroid, and to see what happens in direction, look at the difference, but go to the Fourier transform then, because the Fourier transform tells me the spectrum of directionality. So I take this representation of the coherence function in centroid and difference coordinates, and do a Fourier transform in the difference, in the separation variable. And that will give me a function that is a function of position, direction, and distance. And this is something that was discovered independently in several areas of physics, but it keeps the name of the first proposition, which is Wigner. It's called the Wigner function. It was reinvented in optics several times, actually. It was reinvented in signal analysis, but Wigner was the first one. Proposed it with very different language, thinking about quantum states. And surprisingly, in paraxial, and I should say it's paraxial free space, it satisfies exactly this property. It satisfies exactly this property of the radiance that we saw, of the light field. And it also satisfies exactly this property. The marginal gives you the intensity. So this is a great candidate for ray-based description in the partially coherent sense, in the sense of a light field of light. There are some catches. And one is that this function is real, that is good, because we're calculating as an integral of these are all complex. So it is real, but it can be negative. And that is a bit disturbing in a way. I'd like to stress that this phase space in this wave sense is a bit like a musical analogy, and there are many aspects in many areas of physics where the same thing happens. So here we have in optics where's the range? I'll go to the other side. So in optics, we have rays, where I have a ray and I can say where it is and where it is going. So I specify x and p, and waves, where I can specify the field in x or the field in p, in spatial frequency, through a Fourier transform. This is more mathematically correct. This speaks more to our guts. The rays are very intuitive. In mechanics, also we have a particle trajectory where I can say what the particle is and what its momentum is. And here we have a wave function of x, or if I go to the Fourier domain, a distribution in momentum. Again, we're getting more and more used to this, but this sort of speaks more to our gut. The intuition that we have from everyday life of classical mechanics is much more clear. A third one is sound, and let me be specific just for the sake of argument, music. And let me start here. Music is sound waves. And I like telling the analogy that suppose that you love this musical piece and you're very geeky, and yet you don't have Shazam or anything, and you want to know the name of this musical piece. So what you do is you print out the time signal of this. And then you go to your friend, the musician, and say, okay, can you tell me what's the name of this piece? And she or he would laugh and say, sorry, I cannot help you. If they are very helpful, they can say, well, it is 3 minutes 45 seconds. It's very intense here. It's very faint here. I can tell you some things about it, but it's really hard. And then again, you're a physicist or an engineer. What do you do when you don't know what to do? Exactly. So you get something like this, and you say, okay, now this will do it. And you run to your friend, say, okay, now tell me. And they say, nah. And they say, well, maybe it's in C major, probably, because we have this. They use some high-pitch instrument, like a pickle or something. There's a lot of bass as well. You can say some things about it, but this is not intuitive. What could you show in a piece of paper to your friend that they would tell you what it is?
Notes.
Something like that. What is this axis? What is this axis? In a log scale? Frequency. So it's time versus frequency. Again, like here and here, this speaks to our guts. This doesn't so much. I mean, it gets some getting used to. And these ignore the uncertainty relation. In music, you can say, oh, I'm in this note, and I'm going to make it really, really, really short. And you can know, it shows through simulations that if you make a note really short, it stops being a note. Because it's so short in this duration that it spills over the other notes. So you ignore the uncertainty principle, but it is very intuitive. So that is the idea of the Wigner function, is to represent things in this way. It's a compromise with many catches. And it's not the only alternative as well. So if you're interested, I wrote some review article about this, particularly for the optics realizations. Well, more than a review, it's a tutorial. And it tries to give a picture of all these representations.
So here the Wigner function is not necessarily positive.
Exactly.
But these are all like classical waves.
Yeah. So
the
let's.
radiance is negative.
Yeah, exactly. So this is exactly what I'm gonna show next. So let's go to the coherent case, which is something like this. So unfortunately, you cannot see very well. I use some colors that is green is positive, red is negative. And there's a red banana-shaped thing here and one here. So this is, imagine a plane wave coming here and hitting an aperture. And that creates a diffraction pattern like this. At the initial plane, the Wigner function is like that. If I do the projection, it gives me the initial rectangle. Now, if I propagate, I just need to shear this space. And then I see that the intensity at different planes are just the projection of this. So we've turned propagation from quadruple integrals to shearing and one projection. Although we don't have the phase, we're just getting the intensity. This maximum here, so there are these negatives here that we cannot see very clearly. I should use the log scale. But when those negatives align, like around there, there's a negative here like this and a negative here like this, they align. And when I do the projection, they reinforce the negative contribution that cancels almost this positive contribution, and we find this dip in the intensity. So to model diffraction effects, we can do it exactly in the paraxial regime in terms of rays, in terms of a light field, but we have to bite the bullet that there are anti-rays, that there are rays that eat light, let's say, that carry a negative amount of light. You can never isolate them. Any measurement you would do would be a projection or some overlap that is guaranteed to always have more positives than negatives. And whatever you do is guaranteed magically to always give you something positive.
Then the phase information we have.
The phase information is going to be hidden in those negative rings, and I'll show some simulations for that. Yes?
That was my question. Your anti-ray is just something that's out of phase.
Well,
The opposite phase.
when I explain this to the photographers, phase means in a way nothing to them. It's a ray that is carrying some amount of light, and light is some amount of energy or something, and that usually is positive. But we can keep using that language of the light field, but we have to allow for these negative rays. So they're out of phase because they're negative, but it's not a phase in the sense of the field. These quantities are intensity-like. The Wigner function has the field and its complex conjugate already. So the phase is not a phase. The function itself is real. Does that answer the question?
Yes, but what we see there is simply disruptive interference.
Yeah, absolutely. So said in other ways, these negative rays is the only means that this picture of the Wigner function in terms of rays has to account for destructive interference. And similarly,
One more limitation, right? Because the factor of 2, your frequency space cuts by half.
yeah, so that's a practical limitation.
Practical.
Yeah. And similarly, if this were, for example, the pinhole of a pinhole camera, we know that for a pinhole camera there's an optimal distance to put the screen, depending on the radius of the pinhole. And here we can see that it's this, and that it corresponds to the place where these positive branches align. So there's some intuition there as well. So just to show you the same thing in a different point of view, and let's see if this works. I'm going to show here, I'm going to put a gray background that it represents 0. And I'm going to just start drawing rays, nothing but that. So I'm going to start putting some rays. I put a ray here. I'm going to sample. In reality, I have a continuum. And I make the rays white if their Wigner function is positive, black if they're negative, and I give them a transparent opacity that is proportional to the magnitude of the Wigner function. And I just start putting one on top of the other, more and more and more and more. At some point, and this always looks better on my screen than on the projector, but you start seeing the diffraction pattern here. I did nothing nothing non-ray optical here. I drew lines with different colors, with different black or white and different opacities. The integration is just the superposition of those. Of course, ignore these artifacts from my sampling, but what you see is that you just putting these lines, doing this superposition of the contributions from different things, you recover the wave features.
So you seem to be recovering like the Fresnel regions also. Fresnel
Yeah, yeah.
And those are like this nonlinear phases.
Yeah.
So those seems to be being carried over.
Yeah, yeah, yeah.
And that's quite magical.
Yeah, it is quite remarkable that it was. Okay.
You said you're ignoring the uncertainty here. So are you really ignoring the uncertainty, or
No,
uncertainty is there in some
no,
sense?
no. I'm ignoring it here, but the Wigner, all the structure of the Wigner, which I will show now, maybe I should do that after this slide. It is inbuilt there. So the fact that not any function of x and p is a Wigner function. The Wigner function has strict rules for what it can do, and those account for uncertainty. And things like these negative wiggles are a key aspect of that. So just one last thing before I change to a different presentation to show something else to do with the phase, etc. This is just, no, this is what I just showed you. Need to go to the next slide. So at some point I was curious about what happens when you have diffraction. So you can think that, well, I can just keep using the Wigner function. I just let the rays that pass through there keep going. The ones that are stopped by the optical stop. Of course, that would be the standard ray optical light field type of thing of modeling the penumbra caused by an obstacle, etc. But how do you add the diffraction effects? And similar to what I discussed before, you have to think of diffracted rays. Although here they behave a bit different, because we're in a partial coherent field, there's a whole range of rays that hit the edge. And you have a range of rays that come out. And this edge does sort of a remix of this. If I have an angular distribution here, it turns out that this distribution is minus the derivative of the Hilbert transform of that distribution. And that would create a distribution of rays that you have to add by hand that will quite, to within some approximation, include the diffraction effects. Okay, let me just to address some of the points that were discussed, come to this these slides that I just stole from that article. So where's the thing to launch it? Yeah.
It should be on the right. I think this side.
Yeah, and on.
Yeah.
It was all the way to the end. That's why. The bottom of my screen doesn't work, so I don't see it here. I have to look. There we go. Okay, so this is just. I'm going to talk quickly. As usual, I'm running out of time. About how to define an alternative to the Wigner function, which is called the spectrogram, or the Buscemi function, or the Q function in quantum optics, or just a window Fourier transform. So one way to get a phase space is I have some function, complex function, blue is real part, red is imaginary part, and to see what happens in different parts, I just put a window that I slide, and each time at each position of this window, I get the product, and I Fourier transform it. So it's like a local Fourier transform. So if I move this, let this window move. Now I'm going to see that it overlaps with this, the Fourier transform Gaussian. Here it overlaps this, and this because of the phase. Right here, I get the overlap of this with this is this complex thing, and the Fourier transform of something with a phase is something shifted. So this would give me two Gaussians in phase space, one at the x-axis and one shifted up. The Wigner function does not use a window, because this representation is nice, but it's arbitrary in that what window do I use? In quantum optics, there's a natural choice, which is the coherent state. But if you're in a more general case, well, this spectrogram You can use a square, you can use a Gaussian, but of what width? You have to make some choices. The Wigner function has a similar, this is how this Husimi or a spectrogram would look for these two Gaussians, depending on the relative phase between them and their separation. So if they're quite, if I change the phase, there's going to be some interference fringes there. But then once they're far away, I can change the phase, I see nothing. So I would see these two blobs. Let's show that again. But it is very easy to interpret. I see these two blobs very clearly. For the Wigner function, I can do a similar definition, but now I need, instead of using a window, I use the same function inverted and complex conjugated. And you can convince yourself that you will get the same two blobs, but you will get, so you see you get interference. For any position, you would see the two blobs, and halfway between them, another blob with fringes that are positive and negative. Their position tells you the phase between the two things, no matter how far they are, and they always point in the direction between them. So if you have 2 or 3 blobs, you have something like this, and the marginals always work. So the good thing is that you have all this phase information, very easy to retrieve, at the cost of these negative things. The problem is that you have a simple field. The Wigner function can look very complicated, and it can, if we think of 4-dimensional space, sampling a 4-dimensional space of highly oscillatory things, that is not so much fun. So, for example, for the type of fields that we were talking in the previous days, where we talk about rays that are along the curve, the Wigner function would mimic this curve, but every time there's an intermediate point of 2 points of that curve, I will have some wiggles here. The phase of the wiggle is proportional to the area enclosed between them, and the amplitude is proportional to some density of if you do replicas of the initial curve that you slide, you get some intersections, and that density gives you the amplitude. So this is a catalog of different phase space representations. For a phase space curve that is just a parabola, the Wigner fills into all these ripples like this. The spectrogram for 2 windows, like we can see that if we choose the window rod, this looks pretty nice. This looks less nice. And this is another representation called the Kirkwood-Rihashek, which is not as widely used. There's a whole family of these things that is called the Coherent class of representations.
So,
yeah.
So this Wigner functions, one can also use them to express like averages of the fields of different multitudes.
Yeah. So
similar quasi-probability.
Exactly. So
aren't there, like, even in this classical picture, aren't there then questions of reality, like these probabilities are going negative?
So I think in this case, so you cannot measure directly for the Wigner for a size of the space where the function is negative.
Effectively, the intensity is negative.
Yeah, the intensity is never negative. But just like in quantum, you can say how negative this is a measure of your quantumness. In optics, this is a measure of your coherence, the coherence of your field.
Non-classicality.
Non-classicality in a more old-fashioned way is how coherent it is, and therefore how not corresponding to the classical light field description. So the capacity of interference. So yeah, these are just an artifact for being able to reproduce constructive and disruptive interference. So just to make a connection with what we said before, this is the airy beam that bends here, propagates without changing, and the Wigner function is concentrated on a parabola, and it has these fringes here. And again, the projections of this give me the zeros even of the airy beam. Now, the interesting thing is, what happens with this parabola when I shear it to propagate? It turns out that if you shear a parabola you get a parabola of the same width, just is up and shifted. It's hard to see. I mean, your eyes almost want to see this just displacing rather than a shearing, but it's really a shearing that is happening. So the projection is going to look exactly the same. It's just going to be displaced. And the more you shear, the faster it goes. The next one is one that you asked me about yesterday, so I included it. The Talbot effect, which is another form of self-similarity. So suppose that you have a periodic field here. You let it diffract. It gets complicated quickly, but there's a magic distance at which it reconstitutes again. And in fact, halfway through that distance, you get exactly the same distribution, but it's completely out of phase. So this seems like a very wave optical thing without classical analogs. Turns out that you can calculate the Wigner function for this. It's very singular. It's delta-like in P, periodically. And what you have is every other line is all positive, and it's related to the initial distribution, but it's at twice the frequency. But then if you go to the odd ones, it oscillates between positive and negative. Now, what happens when I propagate this? This is going to shear. So if you let it shear, the projections are going to change, but at some point, you get to the same thing, and you get the initial position. And if you go halfway, looks the same, but what was positive is now negative. And then the projection gives me, didn't quite hit it, but gives me something that is very similar to the initial field, but out of phase. So just to get to the end, so the Wigner function is something that we've been discussing with Anand a few times. It's a very good conceptual tool, but very often we abandon it after we use it to understand something. Then we find the shortcuts for how to understand the same thing without the Wigner function. So it's useful, but it's a bit disposable in that sense. But once you, especially for the coherent case, but if you go to partial coherence, where you have this randomness, these inconveniences of the high complexity disappear. So for a coherent field, we said it's enough to think of a curve on phase space, and not this full description. For a partial coherent field, we have to think of areas of phase space, and also the Wigner function will get smoother and nicer. So to show this, I'm going to show, this is what is called a Gaussian shell model beam. There's something called the coherent mode decomposition. Because one-dimensional, the modes are Hermite Gaussian, so I can sum Hermite Gaussians incoherently, and that gives me this thing. So these coherent modes would be the Wigner transform of Hermite Gaussians happen to be Laguerre Gaussians in phase space. And so each one of them is going to be very oscillatory. So they're all very oscillatory, but when I put them together, all the negativity went away, and I have a nice smooth thing. So if I want to use my Wigner function now to propagate things, now it makes sense because it's very smooth. I can sample very coarsely. I have a four-dimensional space, but it's not one that I have to sample very finely. And this is really the limit of the light, this partially coherent.
So on the left you have this one mode, and then
yes, one mode. Yeah.
Some of this 20
the accumulation of them. So if I run it again, I'm accumulating them here, and once you get to this becomes a very, very smooth Gaussian. Much bigger than the uncertainty cell. Okay, so just to finish here. So what about the planoptic camera? What is the planoptic camera really measuring, or any measuring device? is really measuring a sample version of the window Fourier transform of the spectrogram. And it turns out that any spectrogram can be written exactly as the convolution of the Wigner function of the field with the Wigner function of the device, in this case, of the lens length. And this convolution between any two Wigner functions is guaranteed to be not negative. It's guaranteed to not have negativity. And that's why what we measure with a Sharp-Hartman or with a plenoptic camera is always not negative. So just a final note and a bit of publicity, some very old work that I did. The Wigner function fails to account for all these exact shearing when you go non-paraxial. There are analogous applications in pulses in dispersive media, for example, where if you approximate the dispersion as linear, you can use a temporal Wigner function and it also shears with dispersion. But once the dispersion is more complicated, that is not true. We found a recipe for defining new Wigner functions tailored for non-paraxial space or for arbitrary dispersive media that preserve the conservation, that are shear only in propagation. So this is one for a strongly focused field, non-paraxial field. The Wigner function looks similar, but it's not the same. But it has the same two properties of the projection and of the shear. So you have to abandon the classical definition, but there's a unique way to define a new definition that would have that right behavior in these other circumstances. All right, so with that I finished. So Wigner functions allow describing out the fields as a plenoptic function or radiance. And in fact, we can think as this being the formal derivation of what the plenoptic field, the light field is. If you start from Maxwell's equations, the one way to get from Maxwell's equations to the equations of radiance or of the light field is through the Wigner function, or something like the Wigner function. And you can extend the formalism to other situations. All right, so that's it. Thank you very much.
Okay, any other question?
Yes.
So is there a simple way of understanding why, like when you have this Wigner function of the field times the Wigner function of the device,
Yeah.
why that is always positive? Then still the field can be negative.
Yeah. So the way to do it, I mean, there are two answers, and one I don't have. So one is you just write two arbitrary Wigner functions. You write the convolution, so you just substitute, or you give it to a student to do. That's a better way to do it. And then ask them to do change of variables. And once you do enough change of variables, you see that what you get is explicitly a mod and some integral of mod squares. So there is really it's just biting the bullet, doing the calculation, and yeah. So the convolution is just way what you did this place, but really, it's sufficient to show that the integral of b1, let's say of x, and b2, so these are for two different objects, of x, b, dx, dp, is greater than 0. And what, if this is for a coherent field u1, and this is u2, actually what this ends up giving you is the overlap between the fields mod squared. Maybe I'm missing some constants. And this, because it's a mod square of something, then it's guaranteed to be positive. So that's where the insanity principle comes in, because if you want to sample the Wigner function at a point in phase space, you would need this guy to be a delta function. And that would violate the uncertainty principle. If it is a delta function in x, it has to be infinitely extended in p, and that becomes a marginal thing, which is possible. So these marginals are a special case. So it's just a change of variables.
So most of these ripples, as you call it, signal processing is called them cross terms. They are coming because the bilateral nature.
Yeah, sure, absolutely. And those simulations where I had the two blobs show that very clearly.
So there are ways to suppress them also. Right?
Yeah.
Pseudo-Wigner-Willian there. So have you tried?
So for example, the spectrogram is something that suppresses them. And in fact, this coin class, you take the spectrogram, you take the Wigner, you take the others, you go to the Fourier domain, the full Fourier domain of those. Something for Wigner, that's something called the ambiguity function. And there, they differ just by a functional factor, which you can think as a Fourier filtering of the Wigner function. There's another function using quantum called the P distribution, which is also part of this family, but it's highly singular. So that's the ultimate thing that is very useful conceptually in quantum optics, for example, but you wouldn't use it in signal analysis or most real calculations. It's more a conceptual tool than a computational.
Yeah. So you switched on a positive negative of a ray.
Yeah.
Right. What about polarization? As in the sense of, I mean, you could switch on that aspect as well.
Yeah.
But then it will take care of birefringence, this, that, and such.
Yeah.
All that.
And the last paper that I said, we have follow-ups. So we define Wigner functions for non-paraxial fully polarized fields. So the Wigner function is actually, and this ties nicely with several concepts that we discussed in previous days. The Wigner function now is a weight of a ray, but it's a vector. And you would think it had to be a vector locally transverse to this. Turns out it can have a slight longitudinal component, which is an analog of the negativity. It's a slight departure of what you would expect. And if you go more partially coherent, that longitudinal component disappears. Also, this Wigner, this vector Wigner function with polarization, you can break into two parts. Just like the spin, just like the Poynting vector that we defined before. There's a part that is due to the phase structure of the field, and a part due to the spin, to the polarization. So you can factorize it in exactly the same ways. And you can generalize it to birefringent materials. The definition gets a bit trickier, but you can do it. And you see the splitting of the rays for the ordinary and extraordinary. So it gets more tedious, but it can be done.
What about time? Can you include time?
Yeah, absolutely. So I did not have the slides here, but yeah, for the analog in time of propagation is dispersion. So this time space-time analogy people use a lot. So you have a fiber. We know that if the fiber is dispersed, if I send a pulse here, it's going to come out big, spread like this. And that looks like diffraction. If I turn this around, it's like diffraction. And it's exactly the same if we do the approximation of linear dispersion. Propagation in a fiber for polychromatic pulse with linear dispersion is a Schrödinger equation. It's a paraxial wave equation. So it's exactly analogous, and you can use the Wigner function. And in this case, propagation in dispersion is a shearing of the time versus frequency phase space. So you go from this to this. And just like with non-paraxial, if your dispersion is not linear, you can cook up a special Wigner function that would have this property.
I have one more. So since this is a quantum information series, and so you're presenting Wigner function as something that is that gives you much more intuition.
Yeah.
How you can fit everything. So, is there any hope that with Wigner function you can understand, let's say, for example, entanglement, where you do, desperately need some intuitive understanding. So, you think, I mean, even if it's not, experimentally useful, but even theoretically from the perspective of kind of having intuitive understanding, can the Wigner functions be useful there in understanding?
This is very speculative. So if there's entanglement, the Wigner function of the whole thing will not factor, just like the wave function, I guess.
Mm-hmm.
And there might be hope that there might be some reference frame in some very lucky situations where it's factorable, not in particle 1 and particle 2, but in some other reference frame. In that case, it could be useful. But I think in most cases, again, the Wigner function is a great conservative rule that you use to draw on the board and all that, and then you understand something and then say, wait a minute, I could have forgotten about the Wigner function, let's do it this other way. And that also works.
So you were also talking about the pilot wave theory in the very first one.
Yeah.
So, I mean, pilot wave theory was something that David Bohm, he tried kind of explaining, keeping the reality and stuff.
Yeah.
And that is also kind of the aim for these ray-based approach to kind of explain everything into just these rays. But the pilot wave theory kind of fails when you bring in entanglement, two particle and entanglement and so on. So, from that perspective, will this ray-based approach or the Wigner, will that succeed or will that?
I don't know. I remember many years ago hearing about what happens with the Bohmian approach with entanglement and debate of whether it breaks or not. And I remember someone convincing me that it didn't, but I forget their argument.
So far, that's the conclusion. The local hidden variable theories, which is the Bohm's approach, doesn't work.
Okay.
And that's the Bell inequality and so on.
Yeah.
So is that the same thing that? I'm not sure.
Yeah, I'm not sure.
If there can be a.
No, but your question made me think of something else. So one of the first drawings that I did in the first lecture is a focus field. So we have these things, and this represents a wave. And if we just think of the flux lines don't do that. And we would think the flux lines are more obviously related to the wave field directly because they're normal to the wavefronts. The rays, we're not exactly sure what they are, but they work really well. In a way, the Wigner approach resolves this because Wigner we can define strictly valid in a strict way for a wave field. We just have to occupy the false phase space. But the evolution is the shearing, which corresponds exactly to this evolution. So the Bohmian trajectories, which are the flux lines, would not be so easy to interpret, I think, in phase space.
Okay, any other? Okay, so this then concludes this 3-lecture series, but there is one more. There will be an institute lecture on 27th.
It'll be shorter.
At, that won't be this informal and tutorial level that we say but that's at Wednesday 27th, 6 p.m. I think the DORD will send out an announcement. Also, we'll upload all these 3 talks on YouTube and maybe we have a QuIC Talk which is there in the physics website, so we can actually check. So yeah, with that, it's
thank you very much.
Also there, samosa and chai. I think there's some.
Amazing. Thank you so much.
Thank you.
I have to leave.
No problem. Okay, thank you.